Go ahead.
Okay. Hello, everyone. Thanks for the kind invitation and give me this great opportunity to introduce our latest work. I hope everyone is doing well in the special time. And I think we can go back to normal very soon. And I hope I can visit MSU in person in the near future. Today, I will introduce the particle vibration coupling in superfluid nuclei with axial deformation. This work is collaborating with NNM. Okay, this is the outline of my work. First, I will discuss the energy scales and the relevant degree of freedom for low energy nuclear physics. Then I will introduce the covariant energy density functional theory, which connecting the scales of nuclear physics from quantum hadron dynamics to the emergent collective phenomenon. Second, I will present the quasiparticle vibration coupling model, including the formalism and the numerical scheme. Then I will show the latest application to axials deformed nuclei from the benchmark to the spherical case lead-208 to heavier mass neutron-rich nuclei, sequence 38, and application to the heavy deformed nuclei, California 215. In the last, I will give the summary and the perspective in the future. Okay, first, I want to talk about the infrastructure for nuclear physics research, the quantum many-body method and interactions. In the different energy scales, we have different quantum many-body method and interactions. If we look at the atom system, the interactions between atoms and atom, all the interactions between nuclear and the electron is the electromagnetic interaction. And we can use the quantum mechanics and the QED to solve the atom problem. And if we look at the quarks, for quarks, the strong interaction dominated, and we can use QCD or standard model to understand them. For nuclear, it's much more different. The nuclear self-bound system built from several to more than 200 strong interacting fermions. It's too many to use the full body method, and too little to use the statistic method we know. And so there's no good theoretical tool to understand the nuclear system. And for nuclear interaction, it's also much more complex. The nuclear interaction is the residual interaction of strong force. And in the nuclear system, we will meet the strong force, the Coulomb interaction, and the weak interaction, much more complex than the other nuclear physics system. This is difficult for nuclear physics study, but it is also provide us the best test ground for the different theoretical tools and corresponding method. Okay, then I want to talk from the Weinberger's third law of progress in the theoretical physics. We can use any degrees freedom we like to describe the physical system, but if we use wrong ones, we will be sorry. For example, the human height is about 6 feet or 102 meters. The distance between Western Michigan University to MSU is about 18 miles, which corresponding to 10 to 5 meters. If someone asks me how many miles of my height or how many feet from WMU to MSU, I will be confused, not mention the Milky Way. The diameter of the Milky Way is 100,000 light year, which is 10 to 20 meters. Similar, this is a distance scale of the distance scale. And similar, if I can visit MSU in person, the best way to MSU is driving for me. Walking or flying might work, but doesn't make sense. The best degree of freedom for my travel is a car, not my feet, not airplane. For nuclear physics, nuclear systems are about several Fermi large. Using the Planck-Einstein relationship, we can know the energy scales of the nuclear system. Okay, and the energy scale of the nuclear physics covers from kilo eV to giga eV, which covers 6 order of magnitude, which also covered different degrees of freedom from the quark and gluon to the collective coordinate. So we mentioned in the last slide, at different degree of freedom, we have different quantum many-body method, like that is QCD, DFT, and the collective models. Just like walking to MSU doesn't make sense. It's clearly that computing the rotation state in deformed heavy nuclei from quarks and gluons would be too difficult. Since the first principle calculation of nuclei from QCD are still far away, we can treat the protons and neutrons as independent particle, as a fundamental particle in the low-energy nuclear physics. And based on it, we have 3 mainstream models: ab initio method, configuration interaction, and the density functional theory. Each of them has its own pros and cons. Normally, the higher resolution, normally the higher energy means the higher resolution, but the higher resolution usually means higher price tag. The freedom is not free. So in the nuclear physics study, choosing the best degree of freedom and the best degree of energy scale to understand the nuclear system is very important. In the last decade, the first development of ab initio method made it possible to calculate a variety of medium mass and heavy nuclei. But it still relies on the interaction and the renormalization groups method, and it is struggle to capture the collective excitations. The configuration interaction is a local theory, which means the interaction is highly dependent on the modern space. And similar to the ab initio, the size of the modern space is still a limitation. The density functional theory still is the only global theory of nuclear structure and can be applied to all the nuclei with one effective interaction, even not always very precisely. And beyond the Midfield, with the help of random phase approximation, we can have a good description of collective motions. In this talk, I will introduce the particle vibration coupling approach, which consider the single particle degree of freedom and the vibrations as an independent building block for describing the low-energy nuclear spectrum. With the correction of the particle vibration coupling approach, we can have a better description of nuclear single particle levels. Okay, the particle vibration coupling approach is an extension of energy density functional theory. For the energy density functional theory, non-relativistic energy density function like Skirm or Gaussian have been very successful for decades. Therefore, one may ask the necessity to build a relativistic version of such approach. The covariant energy density functional connects the scale of from the heavy mesons to the complex dynamics of heavy nuclei. Imports the Lorentz covariance reviews the QCD mass scales which hidden in non-relativistic treatment and allow simple, efficient compelling explanation of nuclear scattering data and the nuclear properties. Famous example of physical insight provided by a relativistic treatment are the explanation of spin optic force and the energy-dependent optic potential of nuclear scattering up to 100 MeV, which emerged from a Lorentz structure of the interaction. Based on the Lagrange density, we can build the relativistic mean field approximation and consider the pairing force to include the superfluid systems. And beyond the mean field, the relativistic random phase approximation, which can include one particle, one hole interaction, can be used to calculate the Gen resonance. Furthermore, we can consider the quasiparticle vibration coupling to include more correlation. In this talk, I will introduce about it. And in this part, I will give a detailed interaction of the framework of particle vibration coupling mode from the formalism to the numerical scheme. The concept of energy density function theory is a mapping from the complicated quantum many-body problem to a simple one-body problem, which can solve relatively easily. And we simplify the many-body wave function to one slat determinant, and to then find the best determinant to minimize the system energy. From the Lagrange density, the Dirac Hamiltonian can be obtained by the general Lagrange transformation. And the Dirac Hamiltonian describes the nucleon as independent particles moving in effective meson and the photon fields. And we limit our single particle in positive energy, which is so-called no-state approximation. And the green function can be written like this way, which we can say in here, we write the self-energy by the relativistic mean field self-energy. After we build the relativistic mean field, we can consider the superfluid pairing correlation in open shell nuclei. The pairing correlation are due to the short range part of the nuclear interaction and plays important role in the open shell nuclei. In this work, we use Bogoliubov transformation to include the pairing correlations. The advantage of the Bogoliubov transformation is it can deal the mean field and the pairing part in the same footage. Just build the Hartree-Bogoliubov matrix, and we can solve it together. After the Bogoliubov transformation, the particle state turn to the quasi-particle state and change the occupation probability from a range between 0 to 1 near the Fermi surface. Okay, this is a traditional relativistic mean field or density functional theory. Both the non-relativistic and the relativistic energy density functional have had a lot of success for decades, but recent analysis have concluded that the accuracy of mass or other observables have reached a limit. For that reason, we need some extension or continue to find some ways to improve the present energy density functional theory. For one method is density matrix expansion, which we connect the nuclear interaction to density functional theory, which we are adding some complex density dependent term in the energy density functional theory. The other is multi-reference and density function theory, and all this generator coordinate method and all this extension to improve the present energy density functional theory, and also the particle vibration coupling. And the particle vibration coupling approach is a method that combines the random phase approximation and include the one particle one hole correlation in the ground state. The Midfield ground state is independent with a leading order approximation. With the Bogoliubov transformation I mentioned earlier, we can include the pairing force. And beyond the Midfield, the first order excitation is one particle, one hole excitation. This is the one particle, one hole excitation. And this one particle, one hole excitation are corresponding to the collective vibrations and can be treated as phonons. The energy density functional theory can include the one particle, one hole correlation by the particle vibration coupling. And today I will show how we include it. Okay, here I would like to have a little summary for Midfield theory. In many-body theory, the motion of single particle, a single nucleus in nuclear medium can be described by the Dyson equation with this self-energy sigma. In general, the self-energy can be written as the sum of stationary local part and energy-dependent non-local part in this way. At low energy, we can the Midfield approximation, the energy-dependent part of self-energy is omitted, and we only consider the static ones. And in Midfield approximation, if we just use the relativistic Midfield, we replace this static part with the Midfield self-energy. If we use relativistic Bogoliubov Hamiltonian, we replace the self-energy with the relativistic Bogoliubov ones. To beyond the Midfield approximation and including more correlations, we need to consider this dynamic part of self-energy. Yes, that's our work, the way we include the correlations. And in principle, the dynamic self-energy can include all manifold correlation, which is with not any approximation. It's accurate at this step. But obviously, we need some approximation because it is difficult to do them all at this stage. So we need some modern exception to simplify our calculations. The particle-phonon coupling model is provide a rather simple approximation to describe this energy-dependent self-energy. The main exception of this model is the particle state and the low-lying vibration mode are strongly cut and can be compete with simple particle configurations, which means the particle can emit and absorb phonons with rather high probabilities. With these exceptions, a fully consistent description of many-body dynamics is obtained. And we can get the quasi-particle vibration coupling vortex. And this vortex include the single particle degree of freedom and transition and the collective motion motions. Okay, and based on the edge-dependent self-energy, the Dyson equation can be written in this way, and with the job is to get this green function, and we can say we introduce the edge-dependent potential in this form, and in the self-energy, the quasi-particle vortex will loop over all intermediate stage in our calculation, and since the self-energy sigma E is dependent on the edge, the single particle quasi-particle edge, the resulting quasi-particle levels are fragmented, and this is observed in the experimental, and each fragment has a certain spectroscopic factor. And the sum rule expresses the fact that the spectroscopic factor are fragmented for each quasi-particle. When we add them all, it's just the sum rule still keeps the sum of the spectroscopic factor goes to 1, and the energy central conserved if we consider all the fragments. And this is a general idea of quasi-particle vibration coupling approach. And in this slide, let's say the low-lying vibration mode, because we need to include this low-lying vibration mode in our calculation. The low-lying vibration mode can be observed as a giant resonance in the experimental. And giant resonance is one of the most important excitation mode for nuclear, and it can be described as a small amplitude response for external field. The quanta of the vibration energy are called phonons. And in these slides, we show different kinds of collective motions. Particularly, we are interested in quadrupole and octuple resonance. The quadrupole oscillations are the lowest order of nuclear vibration mode. Quadrupole phonon carries 2 units of angular momentum and even parity, and octuple phonon carries 3 units of angular momentum and has an odd parity. The quasi-particle vibration coupling approach has been successfully applied to the sphericals. Here is an example of TIN 120. We can say after we consider the particle vibration coupling, the single particle states have significantly improvement compared to the MF calculation, and much closer, has a better description for the experimental data. The quasi-particle vibration coupling can also give the spectroscopic factors, which are missing in the Midfield approach. But few study has been applied to the deformed nuclear system due to the high computation cost, even though the deformed geometries is very important for the nuclear landscape. Most of the nuclear are deformed. And the deformed of the single particle energy by DFT for deformed nuclear are not accurate either. As we showed in last slides, the quasi-particle vibration coupling will bring the calculated silicon particle and close to the experimental data. So a natural way to think is we can apply it to deformed nuclear system and then improved our calculation result. The low-lying vibration mode can be calculated by the RPA or QRPA equation. The RPA equation are determined the edge of the RPA ground state and excitation state and their transition strings. The traditional way to solve the problem is diagonalizing the QRPA matrix and the X and Y corresponding to the particle-hole transition density and the whole particle transition density. However, the matrix form of QRPA can be difficult to apply to the deformed system due to its tremendous computation cost. The computation cost comes from two parts. First, the residual interaction. The residual interaction is the same effective interaction determined the relativistic Bogoliubov ground state. But in the Midfield, it is a one-body problem because this is the general idea of the Midfield approximation. But in the QRPA, we need to calculate this two-body matrix element. And this two-body matrix in deformed case is very hard to calculate it. And the other difficulty is coming from the matrix. In the deformed nuclear system, the QRP matrix dimension can be very, very large due to the symmetry break. And as we know, the larger matrix is difficult to solve. So this increased fast and made it difficult to calculation. So this too difficult made it very, very difficult, very, very hard to have a system study for collective motion at Midfield level. Recently, the development of the finite amplitude method provide alternative way to solving the QRPA problem, which can avoid these difficulties. The main idea of the finite amplitude method is to calculate the residual interaction in the finite difference method. From the definition of the density function or theory, the residual interaction is a derivation of the Hamiltonian. We can directly do the numerical derivation from the Hamiltonian and insert a small variation on the wave function. In this way, we can solve the QRPA problem iteratively, not directly diagonalizing the QRPA matrix. It will significantly speed up the calculation. And by taking the numerical derivation for the residual interaction, we can avoid the two-body matrix element calculation, which is difficult in the deformed case. By solving the equation iteratively, we can avoid the huge matrix diagonalization. In this way, we can have a system study for low-lying vibrations for deformed system. And this help us apply the quasiparticle vibration coupling approach to the deformed case. And in this slide, I will introduce our calculation. Our calculation has 3 steps. The first step is the solving the relativistic Bogoliubov equation in a self-consistent way to obtain the quasi-particle basis. In our calculation, we use density-dependent point coupling 1 interaction and the separable pairing force. Here, I want to mention why we use a density-dependent point coupling interaction. This is because, as I mentioned in last slides, the finite amplitude method take advantage of the numerical derivation. So it's easier to do this numerical derivation for the density point coupling interaction because it's directly action on the energy density function, do a derivation on the energy density form, and we can get the induced Hamiltonian. And the second step is calculate the photon spectrum and their coupling vertex according their quantum numbers and energy. And the final step is solving the Dyson equation. And in this step, we can get the fragmentation or quasi-particle energy and the spectroscopic factors. So this is our numerical scheme. And here I will introduce its application to the deformed nuclei. And the first from the benchmark to heavy medium mass and heavy nuclei. But before I show the result, I would like spend 1 minute to explain how we calculate the phonon vortex. The idea of quasi-particle vibration coupling model is two type of elementary excitation. Particle state and low-lying vibration mode are strongly coupled. Of course, at the peak of the transition strings, the coupling is most strong. And in this way, we can calculate the multiplication of the two-body interaction and the transition density. And in the FAM, we do the numerical derivation on the Hamiltonian and get the effective two-body interaction and times with the transition density. Okay, that means we need to calculate the transition strings first. At the peak of 8 at this point, where the particles emit and absorb the phonons with rather high probabilities. We calculate this vortex and get a new interactions, new vortex. Okay, then I can show the result. First, we show the benchmarks for the spherical case. To benchmark, we show the dominant state for neutrons and protons in lead-208, which is a perfect benchmark case for spherical nuclei. As I mentioned earlier, we considered all quadruple and octuple vibration modes, which means our G is equal to 2 and 3 with different K. And we compared our result with the relative Bogoliubov result and the experimental result. And we can see the spectrum calculated with the PVC shows a pronounced increase of the level density around the Fermi surface compared to the pure HB calculations. And in some case, the order of the levels inverted. And this is very important. The important example is the inversion of the 2G9 half stage and the 1I11 half stage. And this inversion will give the correct spin of lead-208 ground state. Of course, I would I forgot to mention, this is how we transform the quasi-particle to the single particle energies and compare with experimental data. We use lambda plus the quasi-particle for the state above the Fermi surface and the corresponding lambda minus quasi-particle corresponding the state below the Fermi surface. That's how we transform. This figure shows our calculation result for neutron states of California 215. To compare with experimental data, in spherical case, we only show the dominant fragment. Our self-consistent calculation shows the deformation of California 215 is beta 2 is 0.29. Again, we considered the quadrupole and the octuple vibrations. The relativistic FAM-QRPA calculations review several low-lying phonon modes in both quadrupole and octuple channels coupled to the HB state with considerable strengths. This coupling caused a shift of dominant fragment obtained in the PVC calculations compared to the counterpart HB quasi-particle states. We only kept dominant. Remember, our calculation is fragmented, so we only consider the dominant term in order to compare with available data. And this is because we're assuming that the dominant fragments are more likely to be detected in the experimental. And we compare them to the band height levels in California 251 and California 249, which corresponding to transverse experiment and the knockout experiment. Thereby, we can see the dominant fragment moves towards to the experimental ones, which improves the result significantly. This effect proves the necessity of particle vibration coupling for describing the quasi-particle state in the deformed nuclei. And this is another example for neutron-rich silicon-38. In order to present the effect of deformation, we performed the similar calculation at different deformations from beta 2 equal minus 0.5 to 0.8. This is a wide range from oblate to pollate. The result for the state we plot is still the largest spectroscopy factors one, which is the dominant one. And the right is shows a relativistic Bogoliubov Nielsen diagram. We plot as like Nielsen diagram. And this finite wise, this band of each color is proportional to the occupation probabilities. And the right part is the PVC calculations. And the first thing we noticed in this figure is the signal band in the PVC state. This is indicate a considerable reduction of the occupation probabilities with respect pure Midfield calculation. This is because we only plot the dominant fragment. And we verify this calculation at spherical limit. If we go to the beta 2 equals 0, we can see the degenerate, all quasi-particle degeneracy in spherical case are reproduced. And we can see the occupancy probabilities are maximum at the spherical limit. And the next thing we observed is the additional oscillators. These additional oscillators I will give a detailed explanation in next slides. This is because the evolution of the phonon vibrations at different deformations. And we can see a few quasi-particle states have much derivation from their counterpart Midfield state, which is due to we can see the effect of phonon coupling and the vibrations. And another thing we can observe here is the formation of the new shell closure at n equal 16. Here we can see a new shell gap exist here. And here is the potential surface minimum, where beta is equal 0.3. And here we can see a new shell closure. Okay, this is the figure I need to explain last Nielsen diagram. And in this figure, we show the transition strings for different phonon mode, both quadruple and octuple for different K we used in our QVC calculations. For a clearly view, I just showed the transition strings from beta 2 equal 0.1 to 0.6 because our calculations already show the potential surface minima for silicon 38 is 0.3, and the experimental data also show the silicon 38 has a porate deform. So we have a detailed study for the porate part. And as we can see, the phonon vibrations involved with the deformation, especially for K equal 1 state, as we can see. It has many states, especially at low end part, many vibrations disappears and at small deformation, not like this G equals 3, K equals 3 case. All the transition, all the vibrations are relatively stable compared to the change of beta 2. And this change of phonon vibrations lead the oscillations in our last states because some vibration disappeared at one deformation, and some vibration appears in deformation. And this is how the quasi-particle quasi-particle state involves with beta 2. And here, because we know the potential energy surface minima, beta 2, is at 0.3. So we give a detailed look at the fragment stage here. One can see that a remarkable fragmentation occurs at the Fermi surface. The analyzed structure of the dynamic self-energy implies this split, but not like the spherical case, which usually have a dominant state. In the deformed nuclei, we can get a few competing fragments. This is because the axial deformation together with the superfluid pairing correlation in deformed open shell nuclei induced this considerable stronger fragmentation. Of course, this effect is linked to the fact those two effects lead the formation of collective phonon modes at low edges, as I mentioned in last slide. And the overall trend is, however, similar to the spherical nuclei. The major fragment is moving toward to the Fermi and to the Fermi surface, and we can get better description for the single particle levels. And here is my summary. And the quasiparticle vibration coupling is a method to beyond the Midfield approximation and provide a formal extension of energy functional theory to include more many-body correlations. The degrees of the quasiparticle quasiparticle vibration coupling approach is quasiparticle state and the phonons. And we applied it to the open shell nuclei with axial deformations. We applied it to the medium mass and heavy nuclei, and we see significant fragmentation of quasiparticle state around the Fermi surface, and increase of the level densities in both neutron and proton subsystems, and which improves the agreement with experimental compared to the Midfield approximation. And our next step, or our current work, is introduce energy density potential, this energy dependent potential in response function. And we hope it will lead a fragmentation of jet resonance spectrum due to the complex configuration, such as two-particle, two-hole excitations, and considerable increase of the wells. And another work I want to do in the future is start from the Rare interaction to see the PVC effect in ab initio. Because in principle, after we consider the particle vibration, we need to refit our energy density functional parameters. But this is a huge job, and nobody have ever done it. So, but from the Rare interactions, we can clearly see we can have a better view of this QVC effect, how the QVC include the many-body correlations. And thank you. And this is my collaborators, and thank you them. I also thank their thanks their work. Okay, this is my talk. Thank you.
Thank you for the very interesting talk. Are there any questions? We have some time.
Okay. No.
No, great.
Yeah, go ahead. Okay, then maybe let me start. You're working with in a symmetry broken system. So how important is the restoration of the symmetry, and how difficult would it be?
It's very important if from both sides, because if you don't have the symmetry, the quantum number is different, basically different because the symmetry, because the symmetry break. So if we see these figures in the spherical case, we can only see the 1D 5½ or 1D 3½ stage. But in reality, we can see different quantum numbers. And only with the deformations, we can give a right correction for this nuclei. And of course, if we see the rotation, because nuclear rotations, the spherical nuclear clearly won't rotation at all because it's symmetry. So for spherical nuclear, the rotation is meaningless. Only in deformed nuclear, the rotation have clearly physical meaning, and we can observe the rotation band from the experimental data clearly. Even although the experimental I compared is the band height state, which is the head of the rotation band. So it's very important.
Okay. Are there any other questions? Yeah, Elena, please go ahead.
Yes, thank you. I was wondering if you can comment on the treatment of the spurious states, because I think it's a very important component of your analysis of the low-line spectrum.
Okay. That's a question I hoped, but no, nobody asked.
So actually, I wanted to ask, but since I'm course, I thought I will not ask.
Okay. This figure, I hide something. Clearly at very low low omega. When the omega very small, we can see some very strong transition. And this transition, some transition are physical states, some transition are spurious state. Because FEM, because we calculate the vibration, if the vibration can be spurious if we see from the vibration mode, if the neutron and proton motion in the same way or together, it will generate it's meaningless. The transition is meaningless, but the RPA calculation can give us this transition, and so we need exclude this spurious stage. And in FAM, all the spurious states are excluded, but still have some. We have implementation, some methods to propose to separate spurious response related to the break of transition symmetry from the physical response. And but in practice calculation, it always has some mixing due to the finite size of the oscillator basis. And since this spurious state is caused by the finite size of the harmonical oscillators, which means it must be very sensitive to the parameter of the harmonical oscillator parameters, and we can play with it. So we changed the parameter of the harmonic oscillators. In here, we change the shell number. As we can see, the physical states are relatively stable compared to the change of the shell number of shell, which also shows our calculation is converged with the shell number. But if we see the spurious state, which will give us a very high phonons at very low end, and in PVC, these low end phonons are very, very important. So we must separate the spurious state and the physical state. But in here we can see the spurious state is heavily dependent on the number of shell of the parameter of harmonic oscillators, and the physical state is relatively stable. So in this way, we can calculate, we can changing the parameter of the harmonic oscillators and separate the physical state and the spurious state, because the physical state is much more stable when we change the harmonic oscillator parameters. That's how we separate the spurious state. And yes, this is very important because this low-lying vibration are very important. Okay, Peter.
Yes, I also would like to make a remark here. There are two spurious states. There is a spurious state with respect to translation, which is a K minus, 1 minus.
Okay.
This you can never get in this finite oscillator basis. But there is the other spurious state, the K1 plus, which corresponds to the rotation. And this you should be exactly have at 0 if you run with a basis which is spherical. So this would be a check if your code is right. You run in a spherical basis, which might be not so good for the final description, but it's still rather good. And then you see if this spurious state must be exactly at 0. That's a check for your code.
Mm-hmm. Yes.
It will never come exactly at 0. No, it will. We checked this. Mm-hmm. We did such thing with Peña. We checked that it will, of course, up to 10 to the minus 10 or something. Yes, exactly. But it is machine accuracy. It's a good check for the code. You should do that. I have another question or comment. I mean, your level density is well improved, but still with respect to the experimental situation, there's still some way to go. You have some idea which kind of physical processes this can achieve?
Yes. As I mentioned, in principle, if we include all the manifold correlation in our self-energy, in principle, we can give a good description. But still, the PVC is a simple approximation, and only consider the one vibration state, which is one body, one hole excitation. So we can only see the one body, one hole correlations, and in here we only include the quadrupole and octupole vibrations, and we hope, of course, these two are most important vibration mode, but the easiest step way to see the improvement is adding more vibration modes, and to see if there's improvement, and adding more correlations in our self-energy, energy-dependent self-energy. That's my idea of improve this single particle description. Yes.
Okay.
Well, there is one approximation that we made, which was not really discussed here. And this is diagonal approximation for the self-energy. So I think this can also bring some improvement because in the deformed, especially in heavy deformed, you have a very strong mixing, and adding non-diagonal terms to the self-energy can also bring some improvement.
I think this is also a problem because if you go to deformed nuclei in general, you would expect that the mean field is better than in spherical nuclei. Now here one sees the opposite. Because in the spherical case in lead, it was much more improved if you include particle vibrational coupling. So this is not understood so far, I think. Maybe you are right that it depends if you include more vibrations, but at the end it should be better.
Mm-hmm. True.
Yeah, Jutta, please go ahead.
Yeah, I had a follow-on question to Peter Ring's comment about the spurious state. You said that in a spherical basis, this rotational spurious state, the K1 plus state, is exactly at 0. Well, that's a great check for the code. But if you have a deformed system, you're interested in that. What's the method to get rid of that one? Is it the same method that was just presented here, where one observes how the states change with the change in oscillator parameter? Or is there another way to do that?
Oh, there are many methods in the literature. The Piatov method or the projection method. The projection method, basically, you know the exact spurious state. It's just the momentum or the angular momentum. And so you can basically remove this by projecting it on that value. The components which are on the exact, you remove them. And Piatov has another way to do it. But in practice, they are rather complicated usually to do it. But in practice, one can do that.
Do you have any sense about other spurious states and their importance in the calculations? Is there sort of a hierarchy where you say, okay, at this point, we can ignore the spurious states. They're not going to make much of a difference?
Yeah, if you have separated them, then it's good.
Because in the FAM, we already applied many methods to separate the spurious state, as mentioned by Peter. So this is at least for my calculation, the spurious state didn't exclude is the spurious state bring from the this finite size effect of the HO basis. So I use this way to exclude them. But there are many methods has been applied in the code to exclude this Nambu-Gaussian-Stone motion transition.
When Daniel Peña did a calculation in RPA calculation, and he deformed RPA, and he investigated the convergence if he included more and more components. And at the end, he had to go to 14,000 one particle, one whole components to get it reasonably down. This was a translation. This is always very difficult to get it down. So with these few vibrations which one has here, one probably cannot expect it to be much better.
Okay, yeah, it seems like we're almost out of time.